when I normalize here the sum of squares. Now you'll notice that this is a departure from the paper, which uses 1 over n instead, not 1 over n minus 1. There m is our n. And so it turns out that there are two ways of estimating variance of an array. One is the biased estimate, which is 1 over n, and the other one is the unbiased estimate, which is 1 over n minus 1. Now, confusingly, in the paper, this is not very clearly described, and also it's a detail that kind of matters, I think. They are using the biased version at training time, but later when they are talking about the inference, they are mentioning that when they do the inference, they are using the unbiased estimate, which is the n-1 version in basically for inference, and to calibrate the running mean and the running variance, basically. And so they actually introduce a train test mismatch, where in training they use the biased version, and in test time they use the unbiased version. I find this extremely confusing. You can read more about the Bessel's correction and why dividing by n-1 gives you a better estimate of the variance in the case where you have population sizes or samples from a population that are very small. And that is indeed the case for us because we are dealing with mini batches. And these mini batches are a small sample of a larger population, which is the entire training set. And so it just turns out that if you just estimate it using 1 over n, that actually almost always underestimates the variance. And it is a biased estimator, and it is advised that you use the unbiased version and divide by n-1. And you can go through this article here that I liked that actually describes the full reasoning, and I'll link it in the video description. Now, when you calculate torch variance, you'll notice that they take the unbiased flag, whether or not you want to divide by n or n-1. Confusingly, they do not mention what the default is for unbiased, but I believe unbiased by default is true. I'm not sure why the docs here don't cite that. Now, in the BatchNorm 1D, the documentation again is kind of wrong and confusing. It says that the standard deviation is calculated via the biased estimator, but this is actually not exactly right, and people have pointed out that it is not right in a number of issues since then, because actually the rabbit hole is deeper, and they follow the paper exactly, and they use the biased version for training, but when they're estimating the running standard deviation, they are using the unbiased version. So again, there's the train test mismatch. So long story short, I'm not a fan of train test discrepancies. I basically kind of consider the fact that we use the biased version, the training time, and the unbiased test time, I basically consider this to be a bug. And I don't think that there's a good reason for that. It's not really, they don't really go into the detail of the reasoning behind it in this paper. So that's why I basically prefer to use the Bessel's correction in my own work. Unfortunately, BatchNorm does not take a keyword argument that tells you whether or not you want to use the unbiased version or the biased version in both train and test. And so therefore, anyone using batch normalization, basically in my view, has a bit of a bug in the code. This turns out to be much less of a problem if your mini batch sizes are a bit larger. But still, I just find it kind of unpalatable. So maybe someone can explain why this is okay. But for now, I prefer to use the unbiased version consistently, both during training and at test time. And that's why I'm using 1 over n-1 here. Okay, so let's now actually backpropagate through this line. So the first thing that I always
That's it. Next is next is pn diff 2 that we need to calculate. So bn diff 2 is calculating the sum in this across the column range. So we are trying to calculate d loss by d bn diff 2 sum of all the so with respect to bn diff. What I did for the sum. So it's the sum, and we are saying if the value changes in those, I believe it should be 1, means, and then we n is anyway a constant, so I think how it should be is 1 by n minus 1 into that is 1, and we do a summation. I think should be 1 by n minus 1 into, let's see, 1 divided by n minus 1 into okay, and the sum is also required, right? So bn var dbn var. The same gets replicated across. I think I can make डिपेंड्स काउंट्स कितने जा रहा बी एंड इफ टू और कहाँ यूज हुआ I see only one place. That's it. Means this can be one other way of expanding, but deconsum minus expand. $32 cross 64. One by n minus one to is a constant there.
Like to do is I like to scrutinize the shapes first. So in particular here, looking at the shapes of what's involved, I see that b and var shape is 1 by 64, so it's a row vector, and b and div2 dot shape is 32 by 64. So clearly here we're doing a sum over the 0th axis to squash the first dimension of the shapes here using a sum. So that right away actually hints to me that there will be some kind of a replication or broadcasting in the backward pass. And maybe you're noticing the pattern here, but basically anytime you have a sum in the forward pass, that turns into a replication or broadcasting in the backward pass along the same dimension. And conversely, when we have a replication or a broadcasting in the forward pass, that indicates a variable reuse. And so in the backward pass, that turns into a sum over the exact same dimension. And so hopefully you're noticing that duality, that those two are kind of like the opposites of each other in the forward and the backward pass. Now, once we understand the shapes, the next thing I like to do always is I like to look at a toy example in my head to sort of just like understand roughly how the variable dependencies go in the mathematical formula. So here we have a two-dimensional array, b and div2, which we are scaling by a constant, and then we are summing vertically over the columns. So if we have a 2 by 2 matrix A, and then we sum over the columns and scale, we would get a row vector b1, b2, and b1 depends on A in this way, where it's just sum that is scaled of A, and b2 in this way, where it's the second column summed and scaled. And so looking at this basically, what we want to do now is we have the derivatives on b1 and b2, and we want to backpropagate them into A's. And so it's clear that just differentiating in your head, the local derivative here is 1 over n minus 1 times 1 for each one of these A's. And basically the derivative of b1 has to flow through the columns of A, scaled by 1 over n minus 1. And that's roughly what's happening here. So intuitively, the derivative flow tells us that db and div2 will be the local derivative of this operation. And there are many ways to do this, by the way, but I like to do something like this. torch.onceLike of bndiff2. So I'll create a large array two-dimensional of ones, and then I will scale it. So 1.0 divide by n minus 1. So this is an array of 1 over n minus 1, and that's sort of like the local derivative. And now for the chain rule, I will simply just multiply it by dbn_var. And notice here what's going to happen. This is 32 by 64, and this is just 1 by 64. So I'm letting the broadcasting do the replication, because internally in PyTorch, basically dbn_var, which is 1 by 64 row vector, will in this multiplication get copied vertically until the two are of the same shape, and then there will be an element-wise multiply. And so that the broadcasting is basically doing the replication, and I will end up with the derivatives of dbndiff2 here. So this is the candidate solution. Let's bring it down here. Let's uncomment this line where we check it, and let's hope for the best. And indeed, we see that this is the correct formula. Next.
I also calculated in the same way. Oh. That's what I was.
Up. Let's uncomment this line. This is the candidate solution derivatives of dbndiff.
Okay, seems like this might be the issue. Okay, again, approximately these are close. So it was doing 1 by n before and then minus 1 with whole of that. So I have put now this thing in a bracket. So n minus 1 happens and then 1 by n minus 1. And I was doing right. Next is pndiff. If is here. So this is the pndiff, I think. So it's used in two places. So there are two paths going forward. So bnraw will send gradients once here, and then bndiff2 will also send gradients to bndiff, and those will be additions. Okay, so I'll just write it down there. Shape also I need to see first. Okay, so anyway, let's first think of it. So d loss by d bndiff, that's what we are going to calculate. So it will be addition of two things. Okay, one here plus the another here. First will be first is bndiff impacts bndiff2. bndiff2 and how bndiff impacts it. This is one. The other is bndiff, where it is, bndiff impacts bnraw, and then okay. So by d bn raw multiplied by d bn raw divided by dbnf. So these are the two ways that it's going to calculate it. So we know this thing, we know this as well. bndif2 by bdnp, sorry, I wrote here right. So it's just a square. Okay, so this differentiation will be that will be 2, that's a square, so 2 into bndif. That's done. The next is this individual bn raw. Bn raw is equal to, where is bn raw? It is the multiplication of this. So when we see a multiplication, we do the multiplication rule, so it will be d of this by d bn diff multiplied by this plus, sorry, I should write it in a better way. So one of the multiplications comes out, this is what happens, and in this case this is the multiplication that it's usually this value multiplied by gradient of this. We already know it. Okay, anyway, let's do it because we are doing it. Oh, bn diff into this. So these are the two things. Okay, so bndiff impacts bndiff, it's 1, so we get bn var inverse plus bndiff impacts bn var, I don't think so it impacts, so this will be 0, so this will be only this much. So you can write it as d this bndiff2 into, we calculated this here, plus dbn raw, that is already calculated, into this, that is equal to this guy. Okay, the only thing that we need to check is the size of all of these that we are calculating. Okay, shape, shape. Okay. So anyway, that broadcasting will happen, so that will be taken care of. What is the size of bndiff? Okay, so I think this will work. Again, approximately true. No worries. Next is bn mean I. Bn mean I. Okay, I see at only one place. Okay. This will be anyway easier. Okay. If I'm differentiating based on bn mean I, so uh, bn mean I. Oh, impact of bn mean I on bn def, and then impact of bn def on loss. This is what it is. This we already know. This we need to calculate. So that will be equal to, so it's 0 minus 1. So this is equal to minus 1 is one thing we got, and and if so that's what shape. Forgot the shape. So bn mean I that we say should be just a single row, so we need to sum it all across. So it is this one. Yeah, it worked. Bn mean I is also done. Then we need to calculate h pribn. Okay, we have at the rate here. No, sorry, not this one. H previous, so there are two instances. This is easier. shape also I need for all of them. Sorry, I'm playing a music. I need to silent. So what? Okay. So we are calculating this one, right? So here, right, this is calculated. This also we know. Again, we need to calculate this. So, this one. Again, the same case, right? So this will be, but what is this? So the shapes will be different, obviously. We now use 1 by 64 and this thing. So we can do simply dot expand 32 cross 64 and 1 by n will come out. And this will be and this will be plus, and this will be equal to 1. Same will get calculated, right? Come here. an addition of sorry, that's what we are expanding here, right? EMB this is the tricky one. Just give me a minute. We are going to calculate this 3. So based on my calculation, or we can take the inspiration from here as well. If we are doing D D okay, right? So it has to be 32 cross 30. This W1 dot transpose. So 32 cross 64, that is 64, so 32 cross 30 will get dW1 will be equal to the rate dB1 equal to, now the 64 cross 1, right? Sum it across 1. I believe this should work. Let's see. Finally, we have reached EMB. Concatenate the vectors. Embedding. Concatenate the vectors. Oh, okay, this thing. So it's something like I'm differentiating EMB. Differentiating EMB. The view is getting changed, right? I think for differentiate it should all be one. The same gradient should percolate. So gradient of AMB, we need to reshape it in the form of this. Else I don't see any other way. So, I just see this as Else I don't see any other way of it worked out. Last function is XP. I think it is plucking out a 10 variables. Initial, he is taking the data cell. So words are like that. He's taking the first few words. Okay, that is stored in XTR. For each of the variable, right? We have a context vector. So 3 is the size of that. Index, okay. So it is storing the index, basically. So these are the context words in that. Okay, and we are trying to pluck out the embeddings of each of them. Okay, so it is just plucking out. If we have to differentiate with respect to XP, right, all others will be 0 wherever the changes are, right? I don't know how this will get calculated. How this will get calculated. We had all of them as we're plucking out maximum. XP is the list of XP is the list of context vectors that we that come. Not sure how will that be getting handled here. Let's see.
To here. So this is the candidate solution. Let's bring it down here. Let's uncomment this line where we check it, and let's hope for the best. And indeed, we see that this is the correct formula, div2. So this is a relatively simple derivative because this is x squared and then pass. It's just the end of the other here from bn raw derivative for bn div. And bn now backpropagate through this line here. h3 bn, and so it's, and therefore we get into the corresponding element, but it's equal mean I through the zeroth dimension. You'll notice that array of ones multiplying db and diff. So in fact, I can just do this, and that's equivalent. So this is the candidate backward pass. Let me copy it here, and then let me comment out. Damn. Actually, sorry, this is supposed to be wrong, and it's supposed to be wrong because we are backpropagating from a bn diff into h3bn, and but we're not done because bn mean I depends on h3bn, and there will be a second portion of that derivative coming from this second branch. So we're not done yet, and we expect so this will turn into multiple lines in the past, in fact. So the h3bn is going to be scaled by 1 over n thing. So h3bn, so h3bn, and hopefully, so this here is broadcasting propagation of the BatchNorm layer. I copy pasted the line here, and let's just backpropagate through this one line. 32 by, as I mentioned, transpose. I need to transpose by 6 by that, but in the of mcat, and we want to derivative, we want to back so now we just want to undo that. So of the array m, if you pass into that's left to backpropagate through, is this indexing operation here, m is c at xb. So as I did before, I copy pasted this line here, and let's look at the shapes of everything that's involved and remind ourselves how this worked. So m.shape was 32 by 3 by 10. So it's 32 examples, and then we have 3 characters. Each one of them has a 10-dimensional embedding. And this was achieved by taking the lookup table C, which have 27 possible characters, each of them 10-dimensional, and we looked up at the rows that were specified inside this tensor xb. So xb is 32 by 3, and it's basically giving us for each example the identity or the index of which character is part of that example. And so here I'm showing the first 5 rows of this tensor xb. And so we can see that, for example, here it was the first example in this batch is that the first character and the first character and the fourth character comes into the neural net. And then we want to predict the next character in a sequence after the character is 1, 1, 4. So basically what's happening here is there are integers inside xb, and each one of these integers is specifying which row of C we want to pluck out, right? And then we arrange those rows that we've plucked out into 32 by 3 by 10 tensor, and we just package them in. We just package them into this tensor. And now what's happening is that we have demp. So for every one of these basically plucked out rows, we have their gradients now, but they're arranged inside this 32 by 3 by 10 tensor. So all we have to do now is we just need to route this gradient backwards through this assignment. So we need to find which row of C did every one of these 10-dimensional embeddings come from, and then we need to deposit them into DC. So we just need to undo the indexing. And of course, if any of these rows of C was used multiple times, which almost certainly is the case, like the row 1 and 1 was used multiple times, then we have to remember that the gradients that arrive there have to add.
Blocking out, okay.
So for each occurrence, we have to have an addition. So let's now write this out. And I don't actually know of like a much better way to do this than a for loop, unfortunately, in Python. So maybe someone can come up with a vectorized. So let me create a torch.zeros like C to initialize just 27 by 10 tensor of all zeros. And then honestly, for k in range, xb.shape at 0. Maybe someone has a better way to do this, but for j in range, xb.shape at 1, this is going to iterate over all the elements of xb, all these integers. And then let's get the index at this position. So the index is basically xb at kj. So that an example of that like is 11 or 14 and so on. And now in the forward pass, we basically took the row of C at index, and we deposited it into emb at k at j. That's what happened. That's where they are packaged. So now we need to go backwards, and we just need to route demp at the position kj, we now have these derivatives for each position, and it's ten-dimensional, and he just needs to go into the correct row of C. So dc, rather, at ix is this, but plus c equals, because there could be multiple occurrences, like the same row could have been used many, many times. And so all of those derivatives will just go backwards through the indexing, and they will add. So this is my candidate solution. Let's copy it here.
dot zeros. This will be similar to the size of C itself, right? Yeah. Zeros. For each of these, right? Sorry. Index we need to find this is the index of the variable that we are plugging out. So xb is the array that store the context characters. So in that example 114, first character, because that might be the first character. And oh, not the first, means in the indices, right? That this word represent the first index, this word represent the second index, the dictionary that we are preparing, right? From that, it is giving us one first in that dictionary, the fourth index dictionary, and then we're doing it plus equal to
Let's uncomment this and cross our fingers. Yay! So that's it. We've backpropagated through this entire beast. So there we go. Totally makes sense. So now we come to exercise 2.
So we'll do that in the next instance, the second problem. Bye.